Let's go for the most important chapter, mismatches versus strategies. As you may already know that during fabrication processes, there will be a lot of defects. So it will cause the so-called mismatches. But how can deal with them? I conclude the most important strategies in this chapter. What we should care about such kind of mismatches? Simply because during fabrication we have a lot of parametric mismatch. Yeah. And what kind of parameters you need to care about? Almost everything. For example, the width, the length, the threshold voltage, even C oxide, blah, blah, blah. All of them, all the parameters you know, in practice, will get some kind of mismatch during fabrication. So this is what we should care. And as I mentioned, for such kind of physical variations, especially for critical dimensions, those are critical dimensions, right? Especially for critical devices, and then layer thickness, just like what I mentioned, C oxide, because C oxide equals, right, epsilon, the dielectric constant, divided over, the distance, the thickness of the layer. Which layer? For C oxide, definitely the thickness of gate oxide. But for the others, for example, metal 2 and metal 1, nothing will be perfect. Don't expect for each layer you have two parallel planes to separate it. No, sorry for that. If you zoom it out, you will see a lot of roughness. It is not flat at all. No, sorry for that. So never mind for a specific layer or the isolation layer between two layers. Nothing is perfect. The layer thickness will always get some kind of variation. Then we'll mention about the temperature. Okay, TSMC UMC can only control the average temperature, but don't tell them in the oven, right? This point and that point, they have the same temperatures. Oh, sorry for that. It doesn't make any sense. And the other one is the uniformity of the chemicals, especially the chemical solution. Inside the solution 在溶液里面 again, don't expect all those points will have the same density or concentration. Okay, 它们浓度是不会相同的。Again, TSMC UMC, to their best, can only control the average concentration. That's it. For local concentrations, you need to face some kind of fluctuation. 抖动, 扰动. Okay, so all of them will cause some variations according to for your devices, just like for your MOSFET. Not only for on-wafer variations, but also for wafer to wafer, lot to lot. As I mentioned, this is the biggest, right? Then wafer to wafer, then die to die, then on the same die, you still need to face some kind of variations. For currents, how much in absolute value you need to face? Around 30% the most. And how about voltage? Hundreds of millivolts. That is what you need to face. So if you don't pay attention to such kind of parametric mismatch, then the yield or even the performance will be quite awful. 会非常的可怕。好，所以你一定要想办法把它们解决掉。Okay, then it is an everlasting battle between whom? The process engineers and the design engineers. If something going wrong, the designers will say, "Hey, you process guys didn't do any kind of good enough job for us, right? You had better control your accuracy. Your accuracy is so bad, blah, blah, blah." Okay, so for the process engineer from TSMC, what they can say, if you are not satisfied, please go to UMC, Samsung, or Global Foundry. We did our very best already. So for example, Qualcomm and IC designers, they can do a very good job. And how about you? Right? With the same process. Why? They have very good yield, they have very good performance. And how about yours? So don't put the blame on us. And this is the reason why I said this is an everlasting battle. 永无止境的战争 between those two kind of engineers. However, to the end, IC designers needs to accept the truth. If something going wrong, usually it's your own fault. Okay? If Qualcomm engineers can make it, why not you? Right? If MediaTek engineers can make it, why not you? I mean, with the same process, from the same company. Alright? So to the end, we are losers. We need to respect process engineers. They already do what they can. So you need to try your very best. And this is the reason why this chapter is so important. Then to the final of the page. The smaller feature size, the lower supply voltage always make our life harder instead of easier than before. Okay? The device becomes smaller and smaller, the supply voltage becomes lower and lower than before, and our lives becomes harder and harder because you need to deal more impact from such kind of mismatch. That's it. To my memory, somebody said, okay, only to my memory, all right. Somebody says the best CP cost performance ratio is for 90 nanometers. Okay? Below it, you need to face relatively more mismatch than before. You may guess, according to the process evolution, the better process means the better performance. Yes, that means the better metric? No. Okay? Maybe it is correct before this. But beyond this, sorry for that. After 90 nanometers, you need to face more and more mismatches. I'm not talking about the absolute value of such kind of mismatch. No. I'm talking about how the relative one. How much percent? Okay, for absolute value, yes, they become smaller and smaller according to process evolution. But the critical size becomes even smaller, the mismatch. All right, so you need to face more and more percentage for mismatch. So in brief, never mind what parameter you are talking about. I would like to tell you, after fabrication, you need to face something like this. They will mention about the W, the L, right? Or the threshold voltage, anything. Or the resistance, or the capacitance. I don't care, I don't mind. Everything, after fabrication will have something very similar to this. It means what? Nothing will be perfect after fabrication. Okay? After fabrication, you always have such kind of variation for any kind of parameter. So, to their best, again, TSMC, UMC can only help you to tightly control the mean value. Alright? Even for the mean value, don't expect they will produce it ideally. For example, for your MOSFET, we have 5 corners. 5 corners means what? Each one means average value. Okay? So to the best, if you are lucky, you get TT. Oh, you are so lucky because the performance of your NMOS and PMOS both are typical. Though both are ideal. Okay? Got it? If NMOS and PMOS, according to their operation speed, their performance, if they both are ideal, I mean the average value are ideal, then congratulations, you are here. The mean value is for typical. That is the ideal case. Alright? But, for example, if the operation speed for NMOS is worse than ideal value, then you get what? Slow. Okay? If both are worse, then you get SS. That's it. So it means what? According to the 5 corners you are simulating. Sorry for that. At least, unless you get TT. Otherwise, don't tell me. TSMC help you to fabricate the ideal mean value. No. We have 5 corners. Only TT seems to be close to ideal. That's it. Alright? And this is the reason why we have FF, right? Both run faster. SS, FS, SF. Only 1 out of 5 can be considered to be perfect. But even for TT, only the mean value is perfect. That's it. Alright? Don't expect any of the MOSFETs, even under TT, they will be here. No. Don't expect that. Only the mean value. Okay? But the real value, larger than or smaller than the ideal value. That is the ugly truth. Even under TT, don't expect all the transistors will have the same TT performance. No. Only the average performance. Okay? So even under TT, somebody still run faster. The other 50% run slower. That is the ugly truth. I'm really sorry for that. You need to bend down. 你最好弯腰哈，你最好低头。Why? Because for such kind of everlasting battle, we are always the losers. We need to deal with such kind of imperfect. That is our life. That is our duties. That is our responsibilities to deal with such kind of defects. Alright? Anyhow, I would like only to tell you, nothing is perfect. Even under TT, what is perfect? Only the mean value. But don't expect anybody to hit the mean value. No, 50% above it, 50% below it. That's it. Okay, it's really upset. If you are asking me, for example, how about SS? Maybe if this is the operation speed, if, okay, I don't care what parameter you are talking about, then what is the distribution? Alright, the mean value becomes smaller, okay, and it has its own distribution. Very simple. And where is FF? There. Okay, that's it. The mean value is shifted. That's it. Okay, you still have such kind of distribution. If you are asking me what kind of distribution, usually people will tell you we have the so-called normal distribution, 常态分布. Is it true? No. Why? Oh, okay. According to normal distribution, you have skirts below it and above it. Okay? And if you have a look at the definition for normal distribution, those two skirts will extend to infinity, to negative infinity, to positive infinity. So it means what? Never mind what kind of mean value you have. There will be always some portion of the distribution getting negative value. For example, resistance. Oh, in theory, you will get some portion, maybe 0.0000 some percent. Okay, but it's still not zero. It doesn't make any sense, right? Right? So, if you are if you are so picky about the distribution, allow me to tell you, log normal will be the best for you. Okay? But what is log normal? Okay, just Google it by yourself. Alright? It is much closer to the truth. However, if the deviation is not so big, then log normal can be approximated by normal distribution. Okay, and this is the reason why people always use normal distribution to describe such kind of parametric variation, but it is never be true in theory. That is only for approximation. Okay, keep this in mind. All right, so you can see what you would like to have, just like humankind. The slimmer, the better, right? On the contrary to this, people always like that. Not only for humankind, but also for our parametric distribution. The smaller standard deviation, the better. Okay? Not only for humankind, but also for our process variation. We hope the smaller standard deviation, the better. Got it? To measure how bad or how good the distribution is, we need to apply such kind of standard deviation. The smaller standard deviation, the better. That's it. Okay? That is the big difference between TSMC and the others. TSMC try its very best to reduce, not to control the mean value, sorry for that, but to control the standard deviation. With the same process, again, for example, 5 nanometers, if you get the process from TSMC after fabrication, I promise you, the standard deviation is smaller than Samsung's. And this is the reason why Qualcomm faced a lot of trouble nowadays. Okay? Yesterday I read the news. If you put the order to Qualcomm, for some, maybe for telecommunication or something like that, you need to wait 50 days? No, sorry for that. 50 weeks. It's almost 1 year. Okay, you put the order right now, then 1 year later, go to the company to get the chips. Wow, that is really troublesome for Qualcomm and many of the others. And how about MediaTek? Oh, that is really lucky because from the very beginning, it cooperated closely with TSMC. Okay, so in the same news, I heard that from MediaTek, if you put the order right now, then about 30 weeks you can get the chips. 30 weeks is still a long time. More than half year, right? But it's still much faster than Qualcomm. Then the competition between Qualcomm and MediaTek. Right now, it seems Qualcomm lost a lot of battleground to MediaTek. Not according to its technology, no. According to its bad policy, because it put most of the eggs into Samsung's basket. 他把太多鸡蛋放到三星的篮子里面去。That is their own fault. Okay. And I also heard that the production of TSMC in next year, not for this year, no, for next year, is almost 100% booked. Alright? That is really good news. Okay, so how to measure how bad the variation, the distribution is? We have such kind of mismatch according to standard deviation. Mean value plus 3 standard deviation. We call it 3 sigma. Okay? So to the semiconductor industry, you need to promise less than 1% of the value is beyond 3 standard deviation. It means within 3 standard deviation, you need to get more than 99%. Okay? My youngest brother worked for TSMC, maybe more than 10 years ago. Anyway, he retired already because he made good enough money to live happily since after. He told me, what is the very fundamental requirement from his manager? To the end, he was also some kind of manager, in TSMC. The requirement is less than 1% is not for this, for only 1 sigma. Okay? From the very beginning, TSMC required that beyond 1 standard deviation. The others beyond 3 standard deviation. You can see how hard their life is. That's it. Okay? But finally, gradually, TSMC became the top of the top, the best on earth. Never mind how much money, how much resource Samsung or Intel pour in. You can see TSMC is still the best on earth. Alright? It also means that you can make a lot of money from TSMC, but you need to face the most challenge on earth for chip fabrication, because their requirements are much tougher than all the others. Okay? Nothing is free, you need to pay for it. More money means what? More trouble, more responsibility you need to face. Alright, but why we have such kind of mismatch? According to the mechanism, we have 2 major ones. First of all, we call it systematic mismatches, just like what I told you in last chapter. For example, oxidation. Inside the oven, we have a lot of wafers to get oxidation at the same time, but oxygen in here, out of there. What I told you, here will become thicker. I mean the average value, okay? Thicker to thinner to the thinnest, right? For the same wafer, because oxygen needs to diffuse in, right? Then to the middle, they can get oxidation. So according to thickness, thicker to the boundary, thinner in the central area, right? I told you, the thickness always look like that, right? That's it. That is the so-called systematic mismatch. All right? That is your destiny. 那是你的命运。If you are here, I mean to the border, to the boundary of the wafer, you will get thicker oxidation. If you are lucky in the middle, then you will get thinner oxidation. I mean the average value, okay? Then that is the destiny. You cannot change it. That is the so-called systematic mismatches. We have a lot of issues according to that. On the contrary, we have the other kind called random mismatch. So if you zoom it in, even in the middle, don't tell me two transistors here, they will have the same thickness. Oh, sorry for that. As I mentioned, if you zoom it in, okay, you will see a lot of roughness. All right, so I'm here, you are there. Don't tell me you are thicker or thinner than me. No, on average, we are the same. But to the detail value, who knows? Because we need to face such kind of roughness. It happens randomly, right? So you need to face random mismatch. All right? That's it. Random mismatch is caused by many of the mechanisms. For example, the ion implantation. Oh, to dope, this is the gate, and then you have source and drain, right? Many of ions are implanted into the surface of the chip, right? How many ions you will get? How many you will get? Who knows? TSMC again can only control the average value. That's it. Okay? But for absolute value, maybe sometimes I get more. For the other time, you get more. Nobody knows. It happens randomly again. Okay? Yeah, anyhow. So, as I mentioned, yeah, just like age roughness. Alright? According to what? The concentration of your chemical solution. Local concentration won't be exactly the same. Okay? That's it. Just like a game we called Monopoly. 大富翁. During the game, you need to throw the dice, right? Then you get fate or chance. 命运或是机会. For fate, it looks like systematic mismatch. For chance, it happens randomly, right? It looks like random mismatch. If you would like to play Monopoly game, then you need to face both the fate or the chance, right? Similarly, if you would like to design your chips, you need to play with semiconductor industry, then you need to face both systematic mismatch and random mismatch. You need to play with both. You need to deal with both. 你只要玩半导体，你就得面对系统性还有随机性的那个误配。That's it. All right. In this chapter, we would like to deal with this. But most of the part, all right. Some of the part will deal with random mismatch. And for random mismatch, you have only one way out, only one solution. That is what? The device area. Okay? The larger device area, I'm talking about W by L instead of W over L. Okay? 是面积哦，不是除哦，是乘法。The larger device area, the smaller random mismatch. That's it. Okay? Don't tell me, I have some kind of random mismatch. How to deal with it? Oh, very simple. Just increase the device size. Oh, no, the device area. That's it. Okay? No more. That's it. Only one way. Only one solution. But how about systematic mismatches? We have a lot of the so-called layout patterns. for help. All right? The other issue, the other very good example for systematic mismatch is this. For example, you have 4 gates to be fabricated at the same time, right? So where does the chemical solution come from? Above the surface. So you need to etch this portion away, etch that portion away, right? As I mentioned, after reaction, A plus B equals C. No A, neither A nor B. A 跟 B 反正最后变成 C， 通通没了。So the chemical solution will be used, okay, during reaction. So how can you keep on such kind of reaction? We need support, we need backup from above the surface. All right? So anyhow, the chemical needs to diffuse from the above into the surface to keep on going. All right? So here, and there, they look about the same because you have some gap. In theory, the same gap. What is the red part? Photoresist. Okay? And where is the gate? This one, the green. Okay? So you can see for those 3 gaps, they face the same challenge. They can only get the support from the sky, above the surface, I mean. And how about both ends? They can get backup from here or even from there. See? So it means what? As you can guess, we don't need to be any kind of chemistry. No, we don't need. By our own eyes, we can guess it is much easier for the chemicals to diffuse from here and also there. Then what? Then here, and here. Right? Because for all those 3 gaps or spaces, the chemicals need to diffuse through the small gaps. It's harder. And here or there are easier. Easier means what? More reaction you will face. That is, it happens systematically instead of randomly. Right? Right? So what does it mean? Sorry for that. At the boundary, you need to face more chemical reaction. It's more etching, 酸死 acid etching. You need to face at the boundary. More etching means what? Smaller gates after fabrication. But from the beginning, you draw such kind of 4 gates. You simply copy and paste. You draw the first one, then copy and paste to the other 3, right? So layout engineers will always think after fabrication, all those 4 will be the same because I copy and paste all of them. During layout, they are exactly the same. I would like to tell you, sorry for that. After fabrication, 1 and 4 will become slimmer than the middle 2. Got it? That is destiny. It happens always instead of randomly. So we call it systematic mismatch. What you can do? What you can do? Because you expect all those 4 to be matched after fabrication, not only in the layout, but after fabrication, 1 and 4 become smaller than 2 and 3. What you can do? You need somebody to protect your boundary. Got it? So you need to get dummy guys, stupid guys, to help you protect your boundary here, your boundary there. That's it. This is the reason why we always need some dummy during layout. Right? In this way, here and there will have almost the same diffusion compared to the others. And it means what? After fabrication, you will have almost the same size through the help of dummy. Okay, that's it. So, what is the golden principle for dummy layout? The most important rule is the spacing needs to be exactly the same as the inner ones. Got it? 它的间距一定要跟内部一样，不然你就卖做dummy。Got it? That is the golden rule. You need to follow it. And never mind, your polygat is in the middle or to the boundary. If you have a detailed look, you can see they have something called overetching. Again, this is what you draw during layout, but after fabrication, you get extra etching to both sides, right? So we call it overetching. But what is boundary condition? You get more overetching here. Got it? Don't tell me overetching only happens at the boundary. No, sorry for that. It happens everywhere. And it means for all the lines, the width after fabrication definitely will be narrow or smaller than the layout. Okay, I'm talking about here and there. Because according to the reaction, chemicals don't go all in that direction. No, they're in this direction and that direction. And it will cause you the so-called overetching. Or side etching. Okay, sorry. Allow me for rewarding. Those are called side etching. Okay, sorry for that. Side etching. 边边会往内缩. So the width after fabrication is always smaller than what you plot, what you draw during layout. Okay, but the side etching will become much more at the boundary, so we call it overetching. Sorry, that is on for rewarding. 重述一下，名词用错了。Okay, that's it. Anyhow, even though you are not at the boundary, you don't need to face overetching, but you still need to face side etching. Okay, got it. Then we have 2 plots for you for comparison. 3 resistors to be matched. All right, 1 and 2 and 3. Okay, you say, hey, look, I have dummy. Oh, very good. You also have dummy, right? Also very good. And how about the key rule? How about the golden rule? The spacing here will be the same as there. The same spacing here and there. Very good. But you can see the difference to the left and to the right. Anybody tell me? Anybody would like to tell me which one is better, A or B? According to resistors, A or B is better, or they are the same. B will be better. Why? Because you can see, for such kind of unconnected dummy, especially for resistors. Resistor usually means high resistance, right? Right? So if the dummy is not connected, it means what? It is the so-called floating. 浮接. Floating is really bad for CMOS because you will get a lot of EMI. Many of the charges, positive or negative, will jam here. 也会受到正负粒子的干扰. Okay? So it means what? The potential of the dummies during operation will become high and low and high and low. It will generate a lot of noise. To bother the real devices is no good. So you had better what? To shut them up. But how can you shut them up? Connect the black one means contacts, right? So you can connect them to some silent source. Okay? Silent means what? Not so noisy. Clean. This is what I mean. So you had better connect them to clean ground or clean VDD. I think I don't care. Right? Again, it means what? The so-called clean sources cannot be used as your VDD or ground for operation. The VDD and ground for your circuit needs to be different from the clean sources. Okay? For grounding, blah, blah, blah. All right. That is what I recommend you to do. And how about capacitors? Oh, this is a very good example. Actually, it is a really bad example. But you can see from the very beginning, we have 6 capacitors to be protected by dummies, right? And how about the golden rule for dummy? The spacing needs to be the same, right? So, it looks very good. So good to be true. Too good to be true. To protect 6, totally, you have 14. Oh. To protect 6, you make 14 for protection. Oh, that is too much. Okay? So, lesson 2. You don't need to use the same size for dummies. No. The golden rule is the spacing needs to be the same. Okay? But I don't tell you need to use the same size for dummies. No. Those 2 are better than this. I mean according to cost performance value, CP 值. How much you would like to pay, right? And how much performance you can get. I promise you, those 2 are much better than the previous one. To protect 9, we only use some of the dummies to protect them. According to the area, maybe you only use tens of percent. Okay? How much tens? I have no idea. Okay? Yeah. You only use tens of percent to protect it. And here, more than 200% for dummy. It doesn't make any sense. If you are asking me, how about the real performance after fabrication? How about the mismatch after fabrication? This one is better, but it's only a very, how can I say, a little bit better, only a little bit better than all those 2. But you need to pay more than 200%. Right? It doesn't make any sense. Usually, we wouldn't like to have this, especially for resistors, capacitors. All right? But how about transistors? Sometimes you need. Okay? Sometimes you not only need to use the same transistors for dummy. But also you need to apply double dummy. Oh, what does it mean? Not only one dummy, but two dummies. Okay, with the same size. Got it? For what? To achieve 14-bit inaccuracy. That is what I saw from the history. Okay, it happens. It seldom happens, but it did. 它非常少发生，但是它还是确实发生的哈。如果你想追求14位元的精度，透过布局而不是透过 calibration， 那你要使用 double dummy。Keep this in mind. Okay, only for very seldom situations. For example, 14-bit accuracy for matching with layout instead of calibration. Then double dummy is what you are required to. Alright? So anyhow, anybody have any idea? Which one is better? Oh, sorry. The answers is already here, right? But why? Is there anybody who would like to tell me why? The right one is better than the left one, even though they pay about the same price for dummy, right? But according to matching, the right is better than the left. Why? Why? Anybody? Why? My hint is according to the golden rule. Alright? You need to make the spaces exactly the same. It means what? We hope the side action will be the same. Right? So if you look at here and there, if you look at here and there, you can see the difference, right? Right? According to chemical diffusion, here is harder than the middle ones. Okay? And to the right, here will be about the same as here over there. Got it? According to diffusion, this one is closer to this and that. But this one, sorry, is harder to diffuse than this or that. Got it? So it means what? The side etching here is not so much as this and that. Alright? So you have the so-called overprotection. Got it? Got it? That's it. Alright? So everything has some reasoning behind. 所有事情背后都是有道理的。Okay? You need to know the real reasons. Then you will tell why it is poor, why it is better. Not only for all the cases I show you. No. Even in the future, you need to face a lot of challenges, new challenges. You never see them before, right? If you have good logic thinking, you have very good reasoning, then you will have better guess. Okay, I cannot promise you, you have correct solution, but your guess will be more accurate than the others without any sense. This is what I would like to make it, to get more sense that all the students don't join our classes. Okay, that's it. So, lesson 2 for matching. You need to use unit devices. For example, according to DAC or ADC, right? You need to have some kind of minorly weighted devices. For example, you need to have capacitor 1 to 2 to 4, right? And for the students, usually they will think, 1 to 2 to 4, very simple. You have the same length, right? But according to width, 1W, 2W, 4W, that's it, right? So in theory, yes, you have 1 to 2 to 4, but in practice, not. Why? in practice, after fabrication, you will get side etching. Got it? So what is the real value? You can see here, here, and there. Sorry, they are not 1 to 2 to 4. You need to get 2 side etchings here, 4 side etchings there to make them exactly 1 to 2 to 4. Right? So how to make it? With unit devices. 1 devices here, 2 devices, 4 devices. That is the rule you need to know. For matching, again, you need to use unit devices. But why? Because during fabrication, we have side etching. To deal with side etching, you need to apply unit devices. But even you have 1 to 2 to 4, right? You still need to have dummy to protect the boundaries. Got it? You need to pay all the attentions you are required to. And keep this in mind. For your layout, they are only 2-dimensional. But for chip structure, actually they are 3-dimensional. What I'm talking about is, for example, you do a layout according to bird view, right? So what is the length? This. That is the length you imagine during layout. But if you take all the 3-dimensional structure into consideration, the surface is not flat. Okay? So you can see, the real length is longer than you guessed during layout. Got it? That is the bird view layout. But the real structure looks like that. Keep this in mind. Okay? So it means what? If you have 2 resistors to be matched, one just like this, and the other one is totally flat. Okay? The layout will be the same. Because according to the layout, you only have bird view. Alright? But if you look at the cross-sectional view, you will know something going wrong. Alright? So what does it mean? You need to make the overall environment exactly the same. If for the first 9 L1, it needs to go here and downward to the bottom, then back to the top. You had better make the L2 exactly the same environment. L2 also comes from here downward to the bottom, then go back to the top. That's it. Okay? Please keep this in mind. Otherwise, after fabrication, or even before fabrication, they are already different. They won't be matched. Okay? Then the same. In the past, we called it tank. Nowadays, we call it well. Okay, any kind of well, I don't care. All right. We have something called well proximity effect. Well 的进阶效应. Okay. It means what? At the boundary of the well or the tank, in the past we call it. All right. You will get more doping or diffusion than in the middle. That's it. So it means what? If you have 5 resistors to be matched inside the same tank, inside the same end well, all right, then I promise you the doping concentration here and there will be higher than in the middle. Okay? So for the real one to be matched, they had better in the middle instead of at the boundary. This is what I would like to warn you. Well, proximity effect. Why? If you are at the boundary, you will get more doping or diffusion simply because, according to the 3-dimensional structure, this is some kind of cross-sectional view. Alright? Don't expect the impurities, never mind through doping or implantation. They will always go in this direction. Sorry for that. I warn you again and again already. Right? So you can see if some go in that direction, then reflected by the wall boundary back to the well. What does it mean? At the boundary, you will get doping or implantation, not only from this direction, but also from refraction. So the doping or implantation concentration at the boundary will be higher than in the middle. Got it? That's it. Okay? Later I will show you some experimental result from TSMC, the best on earth. Even from TSMC, it shows some result to warn the layout engineers. Again, keep your critical devices far away from the well boundary. 如果你的元件很敏感，那你就滚远一点，不要靠太近不要靠边边太近。Maybe you will ask me, how far I need to go away from the boundary? This is what recommended by TSMC. 2.5. Okay. Compared to what? Depth. The depth of the well, right? You need to keep 2.5 more depth far away. That's it. For example, if the depth of the well is 1 micron, then it means what? You need to keep 2.5 microns far away from the boundary. Got it? That is the fundamental requirement. But in this way, you will see, the area efficiency will be much smaller. This is the well, right? So you need to keep 2.5 far away than the depth. You will waste a lot of area, right? So what we can do in between? Dummy. That is the best you can do. Okay? That's it. Congratulations. You don't need to waste the boundary area of your well. Okay? I'm not telling you no device is allowed if they are close to a boundary. No. I'm only telling you no critical devices is allowed here. But some non-critical devices can be laid out here. Got it? 不是说人都不能住边边的反正比较 critical 的、比较重要的，不要靠太近就对了你可以把大米或其他不重要的列那边。Okay, then we need to get some kind of stress, 压力 according to not only your packaging, but also operation. All right. Anyway, this is some kind of tip. Dual inline packaging, okay, or something. 双排封装或是什么的 Anyway, this is the side view. Okay, the top view looks like this. You have so many metal pins, just like all those. All right, and where is the bell die? 螺钉在哪边? Usually in the middle. Okay, and how can you connect the bell die to all those metal pins? 我们把它称作针脚 They are all pins. Okay, how can you connect your bell die to all those pins? Inside the packaging, you have the so-called bonding wire. 棒线 Alright, so after bonding, don't tell me those bonding will get the same stress as the other one. No. Okay, so after bonding, you will get some kind of stress. 打完棒线之后，你的应力就会变得不一样上下左右都不一样。 Even worse is packaging with such kind of epoxy. Here, epoxy, 环氧树脂. Epoxy actually is some kind of plastic. Alright? So, you have some kind of cavity. After bonding, then you have some kind of cavity. 有一些洞, holes. Okay? With some channel to get epoxy in. Epoxy from the beginning, it is just like gums. Okay? 好，跟胶一样，割安尼啦。Okay? It is not solid, but it is also not liquid in between. Not so solid, not so liquid. So it can squeeze in the epoxy from the small hole to fully cover the cavity, to fully cover the belt tie and all the bonding wires. So you can guess more stress here than there than the other end, right? The stress will come greater to smaller from this end to the other end. That's it. That is what I would like to share with you. Anyway, stress will be caused not only by bonding but also by epoxy casually or packaging. OK? 应力不是只有打棒线会产生连环氧树脂的封装都会。Anyway, such kind of epoxy packaging, that is the cheapest, but it will cause the biggest stress. So if you have a look at the core, the belt die from the beginning, in the middle of the chip, you will see this is the belt die, right? The stress here and there are not the same. Here or there are not the same. According to bonding or packaging, I don't care. Alright? We call it stress. And for such kind of stress, if they are pulled out, okay, to the left and to the right, then the resistance will become higher. If they are squeezed in, then the resistance will become smaller. That's it. So it means what? Your post simulation here, your measurement, real measurement there, right? But this is only for belt die. After bonding and packaging, it will be pushed further from your post simulation. That is what I would like to warn you. Okay? Our lives are so difficult. You need to consider every impact, including stress. Stress is not caused by only bonding and packaging, but also by thermal. By thermal effects, after power on, the temperature of the chip will be increased, right? But what will go wrong? The die itself is composed of silicon. So the thermal expansion coefficient, okay, or coefficient of thermal expansion, it won't be expanded so much according to the rise of temperature. But how about epoxy? Sorry for that. The coefficient is much, much larger, I guess 10 times larger than the stone, the silicon itself. So after power on, the temperature is increased. The epoxy would like to expand, right? But the chip itself says no. It means what? The chip will be pulled away by epoxy. Got it? So totally, you need to face 3 kinds of stress: bonding, packaging, and thermal operation. It will make our life even more harder, even more complicated. But this is the way we can survive. Alright? So this is CT, coefficient of thermal expansion. As I mentioned, for epoxy is 24. And how about silicon? Oh, only 2.5. 10 times in difference. Okay, so never mind, you increase the temperature or you lower down the temperature. Alright, if you lower down the temperature, then the epoxy would like to be shrinked. Right, so they will squeeze in your chip to reduce the resistance. But if you increase the temperature, they will like to stretch your chip to increase the resistance for each device. Oh, that's it. That's really upset. Maybe you will ask me, oh, what I can do? All right. According to anisotropic effect of silicon, isotropic it means it is equivalent in all directions. But anisotropic 非等向性 means the property, the performance is different according to different direction. Okay? So, silicon is anisotropic. It is not isotropic. 它不是等向性。So what do you need to do? For critical devices, according to the stress, I don't care it is caused by bonding, packaging, or thermal. I don't care. I would like only to warn you. They need to have the same orientations. For example, one device here, the other device needs to be oriented in the same way. Otherwise, you have one like this, the other one like that. Sorry for that. Alright? The property from this direction and that direction, they won't be the same. So if they are squeezed or they are expanded, they will face different variation in conductivity. It doesn't make any sense. Alright? So to the end of this chapter, I will tell you something called chirality. Chirality or something 手性. Okay? Right-handed or left-handed. Anyway, anyhow, they need to be the same. For example, to be matched, if I have two in this direction, one in the other direction, then how about you? The same, okay? I have 3 fingers, you have 3 fingers. Then 2 in this direction, the other one in the other direction. Then we can be matched. The chirality needs to be exactly the same. 手性一定要完全一模一样。目的很简单，就是要对付 stress. Got it? That is the only way you can do. And we have the other issue called piezoresistivity. 压阻效应 okay? Voltage and resistance. Yeah, that's it. Oh, so the stress in this direction or in that direction, I don't care. They are, again, silicon is not isotropic. So you can see for N-type, okay, for such kind of piezoresistivity, 压阻, it means the resistance will be changed by the stress or by the voltage as you like, okay? Anyway, anyhow, for N-type, it is maximum according to 100, okay? That is maximum. And what is the minimum according to 110? So it means what? For N-type, to reduce the sensitivity to stress, you had better do such kind of layout or that kind of layout for N-type. Alright? But how about P-type? Really sorry for that. Here or there will be better. Are you happy? Oh, that is too troublesome. So my recommendation is still to match 2 devices. They need to have the same orientation. Or that. Or as you like. Okay? This way, that way, or this way. I don't care. The orientation, 它们的走向 needs to be exactly the same. Otherwise, according to piezoresistivity. They will get different conductivity. Okay? According to thermal effect, you need to do such kind of isothermal layout. 我说什么 ？Iso it means the same. Thermal according to temperature. So your layout need to have almost the same temperature during operation. So this is the simulation. We have some EDA tools to simulate the power consumption of your whole chip. And you can see, oh, it is hotter here, colder there, right? So what is our recommendation? For example, this is some kind of power source, power device, power MOSFET. Got it? The temperature variation hotter from here to cooler. So how to match two devices? This is a bad layout. It is bad. Why? Because the right one needs to face higher temperature. Right? The thermal effect will be more. It doesn't make any sense than the left. Right? So they had better locate at the so-called isotherm 等温线. Alright? If you remove AL, then it will become a noun, 变成名词. So according to isotherm, that is what you need to do for layout to match those two critical devices. Anyway, I don't think during your layout you will know where will be. You won't know the exactly thermal distribution of the whole chip, right? Unless you have such kind of EDA tools, otherwise you don't have the whole picture. So my recommendation is at least you know who will consume the most power. Your power MOSFETs, blah blah blah. Okay? During layout, you will know which part of the circuit will consume more power than the others. Okay, then put your critical devices far away from the power source. That's it. You don't need to know the exact distribution. You don't have any way to make it. All right? Just keep the critical device as far away from the power source as possible. That is the way you can survive. 把你的那个关键性的元件离发热的元件远一点，谁会发热？吃大电流的啦 ，Power MOS 就吃最大电流。Okay, so according to the spatial effect, this is the layout for you, right? 空间效应啊。According to systematic mismatch, as I mentioned, something like this, the thickness to the boundary will be more than in the middle, right? Blah, blah, blah. Okay, so the impact, you get different impact at different location. We call it spatial effect, all right? So the difference, we call it gradients, T2, thicker here, thinner there. You call some gradients. All right? How to describe such kind of gradients? This is a good way. Function f of x and y, actually it describes the parameter according to two-dimensional impacts. All right? So here you have the first order spatial effect. 一阶空间效应 and these are second order. So you can guess, how about the third order? You have this s squared y, xy squared, and that's it, right? You can describe it mathematically. First order, second order, to any kind of order as you like. All right. So for MediaTek, again, it requires their engineers to deal with up to second order spatial effect for critical devices. Keep this in mind. only for critical devices, not for everybody, because it will make the layout too complicated. Alright? Anyhow, to make a good enough layout for critical devices, you need not only to deal with the first order, but also the second order special effect. That's it. Okay.